Hello, guys. I have an addition to the previous video on the homeworks, and it also is a little bit in preparation for our quiz. I will make a separate video for the quiz, but this is definitely also a good review for the quiz on how to use paths if you have to decide whether two graphs are isomorphic or not. And we were dealing at the end of the previous homework video, we were discussing this example number 20, problem number 22, and I had come up with a possible isomorphism, and I told you, yeah, guys, check it. I'm pretty sure it was correct. Now I checked it, and lo and behold, it wasn't. It didn't work. So it took me a little while to. I had to think a bit about myself again too, because and then I realized, okay, it is a bit more subtle than that. So I want to try to do the explanation from the start again, so that it is a bit more of a review. But you should look first at the previous homework solution when I discussed this, and then you can see. It's good to see that I came up with a good reason and a good idea of an isomorphism. There was absolutely nothing wrong with what I was saying. It just didn't work, and that shows you that that's why it's such a hard problem. Even if everything what you say is correct, and you therefore say, okay, this is a good guess. I based myself on the circumstances, and I made this educated guess, and still it was not a good guess. So let me go back on the discussion. How did we start off? And the first thing what we look for is the type of paths that these graphs have. Now, I'm going to warn you, they are going to be isomorphic, and therefore, whatever length of path for every length, we're going to find the same number because they're going to be isomorphic. But of course, we don't know that at start. So we started off with looking at. Remember, we're looking always at simple circuits. We can look at other things than just circuits. It can also be paths, but the first thing that you will look at is the simple circuit, and the first simple circuit that you can have is of length 3. I hope you remember why simple circuit of length 2 does not really exist. Okay, length 3. We saw that there were two, and I have listed them here. In either one has. All right, that's something with my. Sorry, guys, I need. This sometimes happens if I. Okay. This is the wrong one. Sorry, I have to initialize my stylus again. Okay, I got it. So I have, we saw that there are two triangles. These are the two triangles in the left-hand side, and here the two triangles in the right-hand side. They're rather easy to recognize, okay? And so they're listed here and listed here. What this means is we know that one triangle has to correspond to another triangle. So remember, what is going to happen is every vertex on the left will be associated or corresponds to a vertex on the right. That's this correspondence we call the isomorphism, and therefore, likewise, every edge will move. If I move this one to there and this one to there and this one to there, then this edge will move to there. Okay, and so in particular, this triangle must either go to this triangle or to this triangle. Now, be careful. There are three. This A, therefore, could go to this point, to this point, to this point, or to this point, and this point. That's still quite a lot of possibilities just for this single A here. But we noticed another thing, that these two triangles, there are two special vertices on the left-hand side, and they're also on the right-hand side, namely, and these are the ones that I colored orange before, namely, among all the vertices that lie on a triangle, so this A, B, C, H, F, and G, there's only two that lie on a different triangle but are adjacent, and that are these two. Okay, they are lying on a different triangle but are adjacent. None of the others have that property. And the same happens, the same situation is there in H. We have to perhaps see it a little bit, but it's here. what does that mean? That means that the yellow points have to map to the yellow points. Now, which order, we don't know. And then we use this argument that I said, so we're gonna, so yellow, so this is talking about the yellow points, where the yellow points, I'm not gonna write it down, but I'll mark them here again. These are the points that are adjacent but lie in two different triangles. Now you might say, but look, these two here, the two triangles start here, but this makes them different, right? Because this triangle doesn't start here. Yeah, but that's just because I chose to start from there. If you want, I can rewrite this triangle, right? Let me rewrite this triangle, and then you see what you were trying to object is not an objection at all, because this is a path that is now, again, a triangle, but it starts at L, and you see everything is now kind of matched up. Okay. So yellow has to go to yellow, and I'm going to make a guess, because of symmetry, especially on the right-hand side. On the left-hand side, I don't see the symmetry that much, except for if you would, if you consider symmetry along this axis here. So I think that it will not matter where so I'm guessing that A will correspond to L. Let's make it that way. I don't know whether that's the original one that I had before, but let's do it this way. A corresponds to L. Okay, and therefore, so necessarily it follows from that the other one, H, must go to the other one, which was P. Okay, so I want to keep in mind that we have now yellow goes to yellow, but I'm going to make a distinction between yellow 1 and yellow 2. Let's call this yellow 2. So the second one goes to the second one, is yellow 2 here. So visually, I see a little bit better the difference between them. So, so visually, I can see yellow goes to yellow, double yellow goes to double yellow. Then we looked at parts of length 4, and again there were two parts of length circuits of length 4, and they are again listed here. We did that last time, so I hope you agree with me. And one more thing, a special thing happens now. It's different, but it is they have. In the left-hand side, there are two vertices that are on both of those. So let me make them in red. I think they made them red. That is D and E. See, D and E, D and E. And here they are R and N. R and N. So R and N, R and N. This, you see, these are the only ones common in the two parts of length 4, in the two quadrangles. And there are no other parts of length 4. And so, so this makes them again special. Therefore, red has to go to red. And I can make the same argument here. I have no idea. There are no connections. How do yellow and what are the type of paths between yellow and red points? Is there anything special going on? Well, this is a part of length 2. This is a part of length 2, this is a part of length 2, part of length 2, but there are also parts of length 3. This is a part of length 3. You have to see it a little bit. And there are many more like that. The same here. This is the part of length 3. It's a bit better to see the parts of length 3 here, but there's also part of length 2. And it is very symmetrical, so I cannot make any distinction between these two. So I said, and eventually in the previous video I made a wrong choice, but it's not at this point yet that there is a wrong choice. So I can do the same, and I can say, okay, I'm picking, oops, so I'm guessing again, this has to do, so this was for the yellow, this is for the red, because a red has to go to red. So I'm saying D, I'm making that correspond to N. I don't know whether that was the same as I did before, but then it follows. So the next one is now completely determined, because E has to then go to the other red, which was R. Okay, so again, let me visually make a distinction. So the second one is E and the second one is R. Okay, and now I'm gonna, this is where I have to pay more attention than what I did in the last video. There are 4 left. And again, those 4, as far as, well, I remind you, they all have degree 3, so degrees are absolutely irrelevant here. But they all have the same property. Each of these has a yellow neighbor a red neighbor and an undeclared neighbor. And it's exactly the same for all of them. Is the situation here? So this is the red neighbor, this is the yellow neighbor, and this is the undetermined neighbor. And here's the same thing: one yellow neighbor, one red neighbor, and one undeclared. And it's for all sorts. So in that way, there are no distinctions. So I am now gonna think a bit more about paths. And so this is what I'm suggesting. Okay, so I'll do the path in blue. So my path is, I'm going to go from the first yellow to the second yellow. I'm going to do this. Oops, no, that's not what I want to do. I don't want to do it in this color. I want to do it in this color. So I'm going to put arrows. The arrow here is to indicate a path. So if I do it differently, it gets really messy. So allow me to put an arrow. So from A to H, that's going to be my path. And then I'm saying I want to go from the second red from the second yellow to the second red as quickly as possible. What's the shortest path from the second yellow to the second red? So I'm going to write this here. It's a path, the shortest path from, and I'll do it in colors, from the second yellow, so second yellow to the second red. It doesn't matter what I choose. I chose these two, okay? But I want to do this in the same hand. See whether that points out one particular. Is there anything that is therefore fixed by this? Well, what are the paths from this one to that one? There is this path, which is a path of length 1, 2, 3. There is this one. There's a path of length 2, and any other path would be even longer, right? So there's 1, 2, 3, 4. That is a longer path. 1, 2, 3, 4, 5 is even longer path. This arrow, remember, is part of my path and is not part of the graph. I apologize for that, but it otherwise really gets too messy. So there is really one shortest path. So instead of saying shortest path, there's one shortest path, and that is the path goes through. And this what path is this? Let me mark the path here. In this case, so in our here, so perhaps I'll continue here, right? So remember, here is the difference between 1 and 2. Sorry, this in the side here. I'll move it around later. So we have, what is that path? That is the path H, F, E. And what is that perhaps if I get a different situation on the right, then I can tell them apart. But no. There is also exactly one part, and everything else is longer, that goes from the second, from the second yellow to the second red. Oh, I forgot to put the arrow here because I'm going to do the same part right here. Remember, isomorphism does not only preserve degrees and vertices and edges, it also preserves paths. So I'm going to try to trace my path that I created on the left, what happens to the path on the right. And so I'm saying my shortest path, so that's the blue path here, is this way, okay? And what is that in Marset? In this graph, it must be this path. And now we get one of the vertices is singled out by this choice, namely this vertex. That becomes now the blue vertex. That's the unique vertex on the unique path from second yellow to second red. Okay. So and this therefore determines completely. So this is, remember, F goes to Q. So F here, I didn't write down the path here. The path was PQR, right? PQR, and so here this is Q. So F goes to Q. I'm not going to write it down anymore. I'm going to do it with color, so that makes it easier later to well, okay, let me write it up. Okay, so from this conclusion, I say that F has to correspond to Q. So this is not a guess. This is a conclusion that I draw from this observation. Now what? What can we now say about what else is there? Now notice that blue lies on a triangle, and there's now only, we're now really paying attention to the colors, the one that have not determined yet. We have not declared an image to the other side yet, right? Or correspondence yet. So of the remaining three, what is now special given the configuration that I have? Well, this one, because this is the one that lies on a triangle of a red, a yellow, and a blue. right? This one, these two do not have a blue neighbor. So this is the one that has a blue neighbor. So this makes it also unique, and it's the blue neighbor. I'm going to make it a double blue, and what's the blue neighbor in the right hand side is this guy. So G has to go to O. So G has to go to O. There is no choice here. That's how this needs to go. Okay, so now we can play the same game. Well, let's continue our path. Let's go along. In both cases, we go along from now we go from double red to single red. And let's say now, what's the shortest path from single red to single yellow? Remember, we're trying to kind of find a path that kind of goes through everything, and perhaps not everything, but we're trying to find a path on the left that should be going to a path on the right. And so we can do the same thing here. So the shortest path from, since we are, the way we are going, now we go from single red to single yellow in that order, right? You understand why it's that order and not the other order, right? If you see in the picture. Now I want to go from here to there, right? If my path have gone this far, notice I've not gone to this point. As I said, what I'm drawing is a path that does not contain all the vertices. It's not an Euler path. Okay, so an Euler circuit. So okay, we go this. Now, what's the shortest path from single yellow to this? That's this path. Okay, let me mark the path. That is this. So that is DCA. Here, so this is DCA. And on the other side, let's mark it. So from here to there, that is NML. 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 And therefore, again, there is, and I'm going to do this in a different color, purple. One point stands out. Now, like that one vertex on this unique path that I found. This one. Oops. No, I want to do this guy, right? And what is it on the other side? I haven't marked the path yet. So let me mark the path. So from there, and then I go there, right? It's a path from single red to single yellow, and it brings me through M. So it says C has to go to M, and therefore now the whole story is finished. B, which I call the double purple, goes to K, double purple. So now the colors scheme gives me already the correspondence. If you want, I'll write it up here. So what we did, I said C goes to M, so C corresponds to M. That is exploiting this fact, right? And then the remaining assignment is B goes to K. B corresponds to K. All right. So this is now a more diligently chosen correspondence. And so now I still need to check whether this is what it needs to be. Okay. It's a bit tedious, so we're gonna have to make the table. So I'm gonna allow myself. I'm gonna erase all this thing in the bottom here. Okay, so we have seen all this now. The colors hopefully help me. I'm going to even erase this here, although. Why is this not going more faster? Come on. We want to see, we want to know whether this works or not. Hurry up, guys, hurry up. What happened? Okay. There we are. See, this is all not necessary. We don't need this anymore. All that can go. All right. Just don't mess with my thing here. Okay. So I have to make the adjacency matrix here. And also from this guy. So the adjacency matrix from G of G, and here we'll write the adjacency matrix of A. But what is it I'm going to do? I have to list the same order in the left than on the right, as they correspond. So what list do you take? Well, I could take. Let's just take the list. Let's go circle around, right? It's a hexagon, so so on the left hand side, I'm free to choose what I do. I'm just changing. There are two choices I could make. I could go along my spot that I chose, but the problem is that then two are not mentioned, or I can go along this long path. which is different. I could have, see, I chose, when I said to find this particular guy here, I needed to take the shortest path, but I could also take the longer path. There's also a unique path of length 3 from this guy to that guy, and that would be this path. Okay, and then the first one on the path with this one, notice that there's also the same here, right? From double yellow to double red, the first one on the path of length 3 would be this guy, the second one would be that guy. So I could, perhaps it's better to take the circular path. So I'm going to go list them in that order. So A, H, G, F, E, D, C, B. Okay, what corresponds there? Now be careful, I cannot not do the same thing here because this is different. To A corresponds L, so L has to go here. To H corresponds P. To the double blue corresponds O. To the single blue corresponds Q. To the double red corresponds R. See what the colors are so nice now? Single red is N. Single, so I'm here now. Single purple, that, oops. Single purple, that is M. Single purple is M. And then finally double purple is K. So this is the correspondence from the left to the right. This is the isomorphism that I had set up, and I erased it, but the colors tell me exactly what goes to what. Okay. All right, and so now we have to make, well, we have to list the vertices in the same order as we make our table, and we have to do the same here. So okay, so L, P. So let's draw lines here. L, P, Q. No, L, P, O, Q. I was almost. L. Let me first draw the lines and then write, because otherwise I'm going to make mistakes. Okay. All right. So L, P, O, Q, R, N, M, K. I want to repeat one more time where this order came by. I chose something, and it was easiest for me to choose this one. Probably you might have chosen the alphabetic order, which actually is just going the other way around. There's no reason that one is better than the other. Or I could have gone like this, or I can do first the yellow, then the... Any order I choose is fine. What needs to happen is, once I decide what this order is fixed. Namely, whatever this color is, it has to be the same color here. So for instance, let's just, A was a single yellow. Oh, A was a single yellow. Well, then the first one should be the single yellow. This was a double yellow. Well, this is the double yellow. The next one was a double blue. I'm not going to do everything, but just to see. Double blue, and that would go to this double blue, and so on. Okay? Perhaps to do one more, that the next one is a single blue. Okay, single blue. Q is a single blue, and that's then comes a red, right? And then E is a double red, and just to see, R is indeed the double red. And then, okay. Now, since I'm playing with colors, let me continue. And then finally, the purple guys. C is a single purple. Is M the single purple? Yes. P is the double purple. K is a double purple. I hope now it's visually much clearer what is happening. The colors are matching. Now the whole thing is, okay, I might be saying all this, but perhaps I'm still wrong. So now we have to check the adjacency. What is adjacent to A? That is B, H, and E. B, H, and E. H and C. Adjacent to A. B, C, and H. Again, ignore the blue arrows here. Let me perhaps even get rid of them because they are no longer relevant. We used that part to argue how our isomorphism would be, but eventually then we didn't really use the part later on anymore. That you don't think that this is a directed graph. Okay, so yes, and what is happening on L? The neighbors of L are K, M, and P. Notice that that's exactly the same. So what needs to happen, remember, is that every row that I make in the left should also be the same as the one in the right. And that is, at least for the first one, is already correct. Let's do H, the double yellow. What is that corresponds A, F, and G. A, F, and G. And what corresponds to P, sorry, neighbors of P, Q, O, and R. Wait, where am I? Sorry. P, where is P? Here's P. The neighbors are, oh no, that's not R. I know there was something wrong. So the neighbors of P are Q, O, and L. L, that's this guy. Okay, that looks more like it, okay, because this is now, I'm filling in the zeros, but it's kind of silly, right? Because if it's not the one, it has to be a zero. So from now on, just let's put in the one. The neighbors of G are, I'm going to do now the rest of this guy. The neighbors of G are H, F, and D. The neighbors of F are G, H, and E. The neighbors of E are F, D, and where am I? E, B. The neighbors of D are G, E, and C. Okay. The neighbors of C are D. Where is D? D is here. What else? B. Where is my B? B is here. And A. A is all the way here. Okay. And finally, the neighbors of B. Sorry, it gets are C, E, and A. Okay. So now on the left, the neighbors of O are Q, P, and N. Looks good, right? The neighbors of Q are O, R, and P. Yep. The neighbors of R are N, K, and Q. It's almost like bingo, right? And the neighbors of N are M, O. What am I doing? The neighbors of N and R. Look, and you see the pattern is exactly the same. I mean, it helps a bit to put the zeros, and you see better even that the patterns are always the same. Because, I mean, it's not on scale, so to speak, so you have to better see also the zeros to see. So here we have 3 zeros and then 1 0, 1 0. And this one is also correct, and I'm very confident that the last two are also going to be correct. But just for the hell of it, I can do one more, and that's enough, right? Because we know the last one must be correct because of symmetry. So C, the neighbors of C are, oh no, sorry, I did that. The neighbors of M, that is K, where is K? Here is K, L, and neighbors of, and what else? Neighbor K, L, and N. And yay, this is exactly what I wanted. So here is an isomorphism. I'm not saying that's the only one, but this is an isomorphism that that works because I had to pay attention to the details of the parts and how the parts are connected. Now, granted, this is a difficult problem, and this is not easy to come up with this kind of isomorphism, and it's also quite time-consuming to find it, right? It took us a little while to establish all this, and as I said, it's because I now figured it out. It took me a while to figure it out. So don't feel bad that these things are not obvious at all, that you see, I don't see it, Professor, what is this? Am I stupid? No, you're not stupid, it's just difficult. And it takes time, and you have to play around and try. And the first try was, I made good guesses, they were not good enough. And sometimes, even if you make good guesses and they're good enough, there's nothing wrong with them, you still might not get an isomorphism. Okay, so I'm gonna stop here, and then we do also a review for the other for the quiz on isomorphisms between graphs using, among other things, paths. Of course, we kept the other techniques from before as well.